So yeah, this is Decoding Starlight is the name of the Discovery Station, but really this presentation is all the science of spectroscopy. And I am continually amazed by this. It's so beautifully simple and so fundamental. It ties into almost everything that we do in the public observatory and astronomy programs, and it ties into an awful lot of the artifacts. For those of you who are docents giving tours or maybe visitor services, helping people find their way around the museum, spectrographs and spectroscopy play into an awful lot of what we do. So this is hopefully going to give you a nice overview and just a good look at what we're doing. Let me make sure that I'm actually in. Am I actually in PowerPoint? Ah, yay. Okay, cool. So what we're covering today will be sort of what is spectroscopy, an overview and some details. I'll give you a very brief history of spectroscopy. There's some interesting developments that have happened along the way. We will look a bit at types of spectra. We will look at how we view spectra. And normally when we did this training in person, there was a hands-on element. I'm going to try and do a very, very brief recreation of that. We will see how well it works. And then we will look at the applications of spectroscopy, which are among the most interesting parts for me. And then we will look at some connections to the museum. All right, so the outcomes that I have for you, and of course I'm showing this gorgeous photo of a double rainbow because a rainbow is part of spectroscopy. By the end of this, I would like you all to be better able to explain the physics of spectroscopy, at least what it is and a little bit of how it works. I want you to be able to describe the applications in astronomy specifically, although if you know of other applications, you are always welcome to tie those in when you're interacting with visitors. And I'm hoping that you'll be able to help visitors make some connections in the museum to artifacts, to stories, to people, to help give that that relevance piece that we're always striving for. All right, so starting with a question for you to put into the chat. What is electromagnetic radiation? Find your keyboards, folks. Come on. I got one answer. What else have you got? Oh, I see you're getting more technical. All right, so we've got light waves, wavelengths of light, energy often described as photons, waves and particles, waves of the electromagnetic field, oscillating magnetic and electric fields generated by accelerating charged particles. Oh, I love you people. The spectrum, the energy spectrum. Yeah, all right, so these are all getting at what this is, and of course, the electromagnetic radiation is fundamental, far-reaching, all through the universe. We deal with it a lot, so there's a lot of ways to describe it. In short, it is light, and it is energy that moves through space in waves. So light usually means what we see with our eyes. The range of electromagnetic radiation and light is bigger than that, and we'll go into that in a bit. But yeah, so electromagnetic radiation is light and energy that moves through space and waves. All right, question 2. What is a photon? All right, a particle of light, a packet of energy, packets of light, smallest irreducible amount of light. Excellent. All right, so yeah, so photon is what we think of as a particle of light, a particle of electromagnetic radiation. So when we talked about energy moving through space in waves, this photon is the entity that is moving through space and propagating that electromagnetic radiation. Important note, as a couple people have said, it has no mass. What moves from the star to the observatory if the black hole's in the form of a marble? Yes, ma'am, that is it. So it's this nice visualizable thing that it's a physical packet or a particle. That is how we generally understand it. It has no mass, and this gets very weird because sometimes it seems like photons do things that behave like they do have mass. Light can exert pressure. Ask Genevieve, I don't actually understand that part. However, photons have to follow space. So even though they don't have mass, they are affected by the gravitational fields that bend the space around them. That's another trading that we'll be doing next month. All right, third question, final one in this round. What is a spectrum? All the different wavelengths of light, a range of light waves or values, a range of frequencies that can be detected, a pattern of variation, a range. Yeah, these are great. And we use the word spectrum in a lot of contexts in life, not just dealing with electromagnetic radiation. But yeah, no, these are great. Yep, continuous range of values. All right. So in this sense, all of those are correct descriptions of what a spectrum can mean. In this sense, when I use the word, I am referring to the array of wavelengths that are produced when light interacts with an object. So it may be an object that's producing light, it may be an object that is reflecting, absorbing, or emitting light, but the array of wavelengths that come out of that interaction, that is the spectrum. And for clarity, the plural of spectrum is spectra. Just like, as I'm sure most of you know, datum is the singular, data is a plural. We forget that all the time, but data is a plural. All right, so you can rest for a little bit. So spectroscopy is the study of spectra, essentially. It is the study of how electromagnetic radiation, or light, interacts with matter. The picture I'm showing there was taken through a diffraction grading, which we'll talk about a little bit later. And it was taken looking up at 3 lights on the ceiling of the Explore the Universe gallery. And all of those, there's the 3 white lights in the center, and then you see these sort of rainbows stretching away from them. So the diffraction grading is showing those rainbow smears. Those rainbow smears are the spectra of those 3 white lights. All right. Yes, data are plural. Thank you, Mary. Yep. All right. So spectroscopy is all about gathering information from an object spectrum. And there is an awful lot of information in there. That's why we refer to decoding Starlight in the Discovery Station. The Starlight has a spectrum. That spectrum has coded information. And when we pull that information out, we can learn an awful lot. A wonderful thing about spectroscopy is that it is what's called a remote measurement. It's a measurement that can be taken from a distance. There are lab tests and things in science where you have to have that thing on your lab bench, in your lab, you have to have it physically close enough that you can touch it and directly interact with it. With spectroscopy, the spectrum, that electromagnetic radiation, if that light can get to you, if you can see it, you can take it into an instrument, you can measure it, then you can get that information. And you can do that across the lab bench. We use spectroscopy in chemistry to figure out what something is, even if it's sitting right in front of us. But we can also do this with stars, galaxies, things, millions of light years away. And so that's the beautiful thing. It travels these distances. For that reason, spectroscopy is how we know most of what we know about the universe. And this is something that I frequently will say to school groups in Explore the Universe, or I will say it to I'll say it during tours or just when talking to people, even at the observatory. As astronomers, astro means star. We think that we're studying stars. Really, what we're studying is light, for the most part. Multi-messenger astronomy refers to the fact that we can use light and sometimes high-energy particles, like neutrinos and cosmic rays, and now, in the last few years, gravitational waves. So gravitational waves, high-energy particles, and light are the 3 messengers. But most of what we get is light. So we, here on our little planet, in our little solar system, if we can't travel to Alpha Centauri, even though it's the closest star, Proxima Centauri, technically, we can get the light from it and we can get that information. So the way that we have learned most of what we know about the universe is through spectroscopy. I will break apart more of the details of how we do it, but I stand in the middle of Explore the Universe and say to people, this is how we've learned most of what's in this room. So I think it's pretty cool. All right. So spectroscopy can be done using any part of the electromagnetic spectrum. Now, the image that I'm showing is one of many diagrams out there of the electromagnetic spectrum, and it's got three different sort of pieces. So on the top, there is a wave, which represents the wavelength. So photons, electromagnetic radiation, which travels in the form of photons, the photon itself is moving in a wave. Now that photon is always traveling at the same speed, provided it is not going through something, a medium like water or air, something that might slow it down. In a vacuum, in space, light moves at a constant speed. So how many waves that little photon is making as it moves corresponds to the amount of energy that it has. So on the slide, hopefully you can see my cursor. On the left here, we have these long wavelengths. These are radio. And then microwaves, what our microwave ovens use to heat up food, are wavelengths about like this. There's infrared light, which is how our remote controls communicate with our TVs, and this is what we know as heat. This is how night vision goggles work. They use this kind of light. This little itty bitty sliver here, which we've spread out into the rainbow, this is the little bit that our eyes can see. This is what is visible light. It's visible to us. It's that tiny little sliver of the whole electromagnetic spectrum. As we go to these shorter and shorter wavelengths, we're getting to ultraviolet light. This is what gives us sunburns. It can get through clouds, fun fact. We get up here into X-rays with these shorter wavelengths, and then we get up here into gamma rays with these really, really short wavelengths. So underneath this waveform, the numbers correspond to the wavelength, so the distance from peak to peak in meters. So, and then at the bottom is an object that corresponds to about the size of that wave. So radio waves can be as long as football fields. Microwaves can be, again, a wavelength that we could see, you know, an insect or a pinhead. Infrared wavelengths get down to cell or bacteria size. Visible light is somewhere in between. Viruses, which are wicked tiny, are down here in the ultraviolet level. When you get to X-rays and gamma rays, your wavelength is small enough, it's short enough that it's on the order of an atom or even a nucleus size. So, question for the chat. We have long wavelengths over here, we have short wavelengths over here. Is a shorter wavelength over here in the X-ray ultraviolet gamma area, is that higher energy or lower energy? I see a consensus, higher, yes, and I tried very carefully not to give it away as I was talking. So yes, if that photon is moving through space at the same speed, if it has a long wavelength, it's not making quite as many peaks and essentially buzzes back and forth as it is over here. This is like just cruising along back and forth. So the shorter wavelength and corresponding to that, the higher frequency number of waves in a given space, that's your higher energy. So we just want to keep that in mind. I would also like to point out that within the visible light, the red light over here that's close to infrared, this is a longer wavelength, so it is lower energy. Over here to the blue and then purple light, this is a shorter wavelength, this is higher energy. So that will have some implications later on. All right, and today we're going to be focusing on visible light spectra because we can see it and we can do that with visitors. However, you can do spectroscopy and study the spectra all the way up and down the electromagnetic spectrum, and we do that. That is a huge part of how we understand the universe, is from looking at all these different kinds of wavelengths, because that lets us see different things. All right, so an excellent application and fact about spectroscopy, one thing that makes it extremely useful, is that this is the periodic table. This is all of the known elements. This is an outdated one because I know we've gotten up to at least 118. I used to babysit for the couple that basically created the 116th element for their graduate project at Berkeley. They named their kid Adam, fun fact. But the periodic table here, each of these elements, each of them emits its own unique spectrum. So it has a spectral fingerprint. and it is unique to each element. So we can use that, and now I'm going to show you what the spectrum looks like for the first three elements, hydrogen, helium, and lithium. So you want to look at it in the whole sort of broad strip here, and you want to look for the bright lines. There's a little bit of background color that makes a whole rainbow, but there are individual colors that are brighter. And which colors are brightest, how far apart they are from each other, which wavelengths they fall on, that is the fingerprint of these elements. So if I have a gas, I don't know what it is, I make it glow and I look at its spectrum and I see sort of a purple, a deep blue, a cyan, and a red, and nothing else, and I see them spaced apart this way, I know that I've got hydrogen. So this fingerprint, this composition or chemical fingerprint, is a huge hallmark of spectroscopy. It is one of many ways that spectroscopy is useful. All right, so a brief history of astronomy, or rather of spectroscopy. So it's credited with starting with Newton and the prism. This is Newton's drawing of what he did. He took the sunlight, passed it through a prism, spread out the light into its spectrum, and he studied what the colors looked like, what that spectrum looked like. So that was in the 1600s. I have kept meaning to do some more serious digging about earlier experiments with this, since I'm sure Newton was not actually the first to do this, but he may have been the first person in the Western world to write about it and tell people. That frequently is how people get credit for stuff. So from there, and again, this is a very selected set of highlights. This is not an exhaustive history, but it goes back to Newton and the prism and looking at the colors and distribution of light from the sun. Then in 1814, Fraunhofer was spreading out the sun spectrum, and he saw these dark lines in it. He saw a full rainbow, like you would expect from a regular white light source, but he saw these lines of colors that were missing, and he recorded them. He gave them letters. We still use some of those letters today. The calcium K telescope is using a filter that looks at the purple line emitted and absorbed by calcium, but it was the line that Fraunhofer labeled K, so that's why we call it that. The 1840s and 50s, and this is a fun sort of side note for the docents, Father Angelo Secchi, who has a local connection because he spent some time at Georgetown, he was a Jesuit priest and an astrophysicist. He built one of the first spectrographs for use in astronomy. He was looking, again, kind of building on what Fraunhofer had been doing, looking at the spectrum of the sun and looking at the spectra of stars. And he was the first to start making some classes of stars based on their spectral patterns and the types that he saw within those. So Father Angelo Secchi, very worth looking up, an interesting guy. Then in the 1880s through 1924, Edward Pickering, who was at Harvard, he had quite a few people working with him and for him, including several excellent women. You've probably heard of Henrietta Swan Leavitt. She was doing variable star work with him, and Annie Jump Cannon was part of that group. And Annie Jump Cannon took some of the classifications that Angelo Secchi had started, and she built on that. Spectrographs had gotten better and better by that point, so that she was able to see more details in the spectra, and she built the spectral system of types of stars, and we still use a modified version of her system. So the late 1880s to the 1920s was a huge development period in astronomy. A lot of things were being figured out using photography and spectrographs and all of these instruments that were rapidly developing. So since the 1880s, we have been in the realm of what is really astrophysics. And as telescopes have gotten bigger, we've gotten better optics. When we entered the space age and developed the ability to put telescopes into space so that we can get at ultraviolet and X-rays, which, thank you Earth, don't get through our atmosphere. But we can't get a spectrum on something if its light can't get through our atmosphere. So space telescopes that look at ultraviolet light, like the Solar Dynamics Observatory, the Hopkins Ultraviolet Telescope, X-ray observatories like Chandra, which is still going 20 years strong. All of these things have become possible in the later part. Somebody pointed out Herschel. Yep, William Herschel was the one who discovered infrared light. He was running sunlight through a prism, running a thermometer along the colors to see if the colors had any difference. And he's going along from purple to red. He goes off the edge of the red and the thermometer goes up. He goes, huh, there's something here. There is a kind of light that we can't see. So Herschel was among the first, he's the first credited with discovering infrared light and really opening up this idea that there are kinds of light that we can't see and are worth studying. So very brief overview of the history of spectroscopy. All right, so types of spectra. All right, so the first is a continuous spectrum. This is the entire rainbow. So if we look at this, and I recognize if there's any issues with your screen or if you have any issues with color blindness, this can get complicated. I want to point out that when you do spectroscopy, the colors can be useful. They can also be deceiving. The most useful things that you can do in spectroscopy are to look for the distances between bright lines or the extent to which the light spreads out, in addition to or even instead of the actual colors. But what I'm showing here is the entire rainbow from red to purple, no breaks. It's just a continuous smear of color. Then we have an emission spectrum. So this, and I'm showing hydrogen here for anybody who recognized it, this is mostly dark, but there are a few select bright colors. So this is like somebody just surgically removed a few pieces of the rainbow and stuck them by themselves. So an emission spectrum will be little bright lines of color. This is how it will look whether you're using a prism or, as we'll talk about later, a diffraction grading to spread out the light. But you will get these separate pieces of color, chunks of color. That's an emission spectrum. Finally, there is an absorption spectrum. And if you look at these three things, the continuous, the emission, and the absorption, you may notice something that connects the emission and absorption spectra. These are both, the lower two, the emission and absorption spectra, are both for hydrogen. And you will notice that with emission, the bright color red here, it's the same wavelength and color as what is missing in the absorption spectrum. Same with this. So basically, if you take this and add this, you get this. If you add your emission and absorption spectra, you should get a continuous spectrum. So I'm going to go into some details now. Why did it do that? Oh, I must have, oh, right, okay. Thought I had messed up the animation. I was fixing this presentation. Okay, so continuous spectrum, the full rainbow. It is all the wavelengths with no breaks. So it's the full rainbow. There's no dark lines. There's nothing missing. It is the full thing. These are continuous spectra are emitted by a hot object. So a hot object that is glowing, producing light, will make some variation on a continuous spectrum. One example of that is an incandescent light bulb. So incandescent light bulbs work by running electricity through a little spring, making it glow really hot and be bright, and that makes white light. Now, this is a conversation that we often have with visitors at the observatory or at various discovery stations. We'll ask people what color, we'll ask people about rainbows, and I'm going to go ahead and do the next bit here because the sun is an example of a continuous spectrum. At its photosphere or surface, so the part that we see in eclipse glasses, in the Dobsonian solar telescope, obviously with some tinting there from the green glass, but in the sun projection, on the projection screen, we're seeing white light. So if you are at the sun's photosphere, white light just means it is the whole rainbow smushed together. And I like to explain this with visitors as this is the opposite of paint. If you mix all your paint colors together, you add more and more pigment, you get black or brown. Light is the opposite. When you add all the colors together, you get white. Ah, yes, the dark spots. So I picked a photo from a day where there were actually some sunspots. We've all almost forgotten what those are because it's been so long. But yes, the sun's surface is a white light source. So it will produce a full continuous spectrum. An incandescent light bulb will produce a full continuous spectrum. If you have a prism or diffraction grating, you can test whether the lights in your house or in the gallery are truly incandescent or if they are fluorescent or even LED by whether they produce this continuous unbroken spectrum. So this is our starting place. White light, continuous spectrum, it's sunlight, it's incandescent bulbs. All right, emission spectra. So this is where you just have a few little chunks, like somebody surgically removed bits of the rainbow. Emission spectra are only emitting, they only include certain specific wavelengths. Those are the colors you see. This is emitted by a hot gas. It needs to be a gas so that the atoms can move around freely enough. They're not held into bonds. They can move freely enough to do what we're about to show. And they are caused by movements of electrons. So the electrons in the atoms are moving to different energy states. They're tootling, zipping around the nucleus of their atom, but they can be at different energy levels around that atom. And as they change, they will cause these light wavelengths to be emitted. And again, I'm going to show that in a second. So an example would be a gas in a discharge tube. This is a picture of one of our discharge tubes at the Decoding Starlight Discovery Station. There is gas inside this glass tube. We are running electricity through it to energize it and make it glow. And the light that we're seeing is happening because of what the electrons are doing. So my proudest PowerPoint moment, this animation, I am so proud of this. So here's what's going on. I'm just using one plus sign here, but we're gonna say this is a hydrogen atom. So we got one proton in here, and we got one little electron here, and it's in this orbital. But that's not the only level it can be at. There are multiple levels of energy. So I've shown 1, 2, and 3. There are more. We're just gonna stay simple with 1, 2, and 3. So this little electron's tootling around, and it decides, or rather, it can be at this higher energy level. So we're going to say that electron started at this level 3, it's higher energy level. When it gets tired of that, as electrons are wont to do, it decides to fall down to this second energy level. And the thing about these energy levels is that they are quantum. You can be at this energy level or at this one. You cannot be in between. This is no electrons land, you can't exist there. So you need an exact amount of energy. It takes an exact amount of energy to move between these two levels. So when that electron decides to fall down to that lower energy level, it expends the exact amount of energy that it takes, that it's losing in falling to that lower level. The wave that you see going away, that's a photon. So in falling to this lower energy level, that electron lost energy in the form of a photon. The amount of energy determines the wavelength that that photon takes when it leaves. Lo and behold, falling from level 3 to level 2 emits a photon of 656.28 nanometers, or this red color. This is what's known as hydrogen alpha. It is the alpha emission line of hydrogen in the visible spectrum. Jay has listed the names of them. This is the Balmer series is this series of visible light lines. There are others that are in the infrared and ultraviolet. Thank you, Jay. But hydrogen alpha is what's being emitted when an electron falls in this way and releases exactly this amount of energy through a photon. All right, so that was emission. So absorption. Emission and absorption are opposite things, which is why we see opposite looking spectra from that. Absorption is a continuous spectrum that is missing specific wavelengths. So it is what happens when light is absorbed when it passes through a cooler gas. Again, it's got to be a gas so that the electrons and atoms can move around in the ways that I was just talking about, caused by electrons jumping to higher energy states. And an example would be sunlight that we see through the chromosphere. So I said earlier that the photosphere, the surface of the sun, is a continuous spectrum. If we could chill out on the surface of the sun, we would see the entire rainbow. It's a hot object, it's producing a full spectrum, nothing is, stealing that light for us. However, we are outside the surface of the sun, we're looking at the sun through its own atmosphere. And its atmosphere will do this. All right, so absorption, again, animation time. So that little electron is sitting there, and a photon happens to come and smack into it. That photon, lots of photons smack into electrons. If that photon is not at exactly the right wavelength or energy level to be the ticket, I really think of this as the electron's ticket to jump a level. If exactly the right energy photon hits that electron, gives it that ticket, boop, it will jump to that higher energy level. So what that means is that lots of other photons will smack into this electron and nothing will happen. When the one that is that just right energy level to be its ticket to jump, the electron goes, thank you very much, absorbs it and jumps, and lo and behold, that particular color of the continuous spectrum gets stolen, absorbed, and we don't see it. Now, in truth, there isn't none of that color here, there's just less of it, because more of that particular wavelength is being absorbed by these happy little jumping electrons. So here is the spectrum of the sun. This is, rather than trying to show this as one giant long thing that would be, wider than my apartment, it starts down at the bottom here, and these are just rows upon rows of images of that stretched out rainbow. So it goes from left to right, and it goes up, and we've stacked the rows on top of each other so that you can see them more easily in a nice rectangular piece. So that big wide absorption line in the red, that is your hydrogen alpha. So again, the sun has a lot of elements in it, but it's mostly hydrogen. When there's a lot of hydrogen there absorbing those particular photons, you will see a darker place in its spectrum. Here's the hydrogen beta, so that's that sort of cyan greenish color that was the next absorption line in the Balmer series for hydrogen. Here's hydrogen gamma. You might be noticing a pattern. We start from the red end of the visible spectrum, and each absorption line gets a Greek letter. So we have alpha, beta, and gamma. So over here, way deep in the purple, which is very hard to see because this is so close to the edge of humans' visible spectrum that it's rather hard to see, but there is a missing chunk of purple here. That is that calcium K line. So it's what Fraunhofer labeled as line K, but it is calcium absorbing that wavelength, and that's the kind of filter that we use to see the sun in purple light. There's two lines here that are sodium. They are orange. You've seen this color anytime you've seen orange streetlights, because this is the orange that sodium emits and absorbs. There's an iron line here. There's a couple magnesium lines in here. The sun spectrum has all sorts of cool stuff. Those are the major absorption lines that you are likely to see in our solar spectrograph and in a sun spectrum like this. All right, so I tried not to give this away, but it's question time. When we're observing the sun in the H-alpha telescope, what type of spectrum are we seeing? So we just talked about continuous emission and absorption. What are we seeing? Oh, I like the question mark, emission question mark. All right, so interesting. All right, so it was kind of a trick question because the answer is both. Yep, exactly. So the fun thing about the sun is it produces different kinds of light and different kinds of spectra get to us. So when we're looking at it, when we're looking at the sun, and specifically in hydrogen alpha, we're seeing two different things. We are seeing, when we look at the disk of the sun here, we are seeing absorption spectra because the sun's white light is shining through its own atmosphere. So there is some absorption happening by those hydrogen atoms. Now we're still seeing a little bit that makes its way through, but a lot of it is being absorbed. But with something like a prominence here, we're seeing light that's being emitted by that prominence. And the same is true with a filament down here. Yep. So we have absorption of the white light from the photosphere minus the wavelengths absorbed by the chromosphere. And then we have emission from the prominence. All right, so fun fact, we see both. You can get absorption from the filaments. All right, and here is a sort of side view of what's happening. This is my very crude drawing of the sun with its chromosphere and its prominences. I haven't seen prominences that big before, but you know, yeah. All right, so we have light from the surface shining onto the prominence. That prominence is then absorbing and re-emitting it outward, and some of it gets to us. So that is actually, that would be a filament because we're seeing it against the disk of the sun. With a prominence that's up on the edge, the sun's light is shining on it, it's absorbing and re-emitting a bunch of light, and that gets to us. All right. So how we view spectra. Who recognizes this picture? Yeah, this is Dark Side of the Moon. This is the Pink Floyd cover, album cover. And yeah, I'm gonna pause. Okay, so we had a good question. So yes, Jay Miller has a sodium filter that we've used for observing the sun. It looks that orange. It's really interesting, gives a nice view of the surface. And yeah, some of the absorption lines, why are some of them wider than others? That is an excellent question. So in general, when we're looking at, let's go back through all this. So when we're looking at a spectrum, an absorption spectrum, like what we mainly get of the sun, the width of the absorption line basically tells you how much of that particular element is present and is absorbing that wavelength of light. There's a caveat to that though. Within hydrogen, say, those widths are a little bit different because some of these electron jumps are more likely or are easier to happen. So you may have more of them, but the proportion, if you've got hydrogen in your sun and it's sending us the spectrum, the proportion between the alpha, beta, and gamma, like how wide this one is compared to this one, will be constant. You cannot compare absorption line widths between elements. So you have to look at how wide that line is for a hydrogen. And based on how wide it is and how much absorption you know hydrogen does kind of normalized, you can compare the normalized one to this and that'll tell you how much hydrogen, what percentage you have. This looks much wider than the sodium. However, sodium might not have as strong absorption even at a high concentration. So you have to sort of regularize, normalize for each element. But in general, the wider the line, the more of that thing there is. It's just how wide it is for a given composition or percentage is going to change depending on which element you're looking at. And Dennis is saying, does the width relate to variance in frequency, not strength? And that I don't know.
I want to jump. I just wanted to jump in here super quick. There are other factors that come into play here. And a lot of it has to do with things like temperature and velocity of the particles as well, that can affect broadening. There's actually a whole slew of reasons why these absorption lines can broaden. Doppler effects caused by the velocities of the particles, the temperature at which these particles are being excited in the first place. And so I'll see if I can find a good resource to throw in the chat if you want to read about it further.
Perfect. And I did not add links to the end of this one, so I will do that before I share the PowerPoint. And yes, magnetic field. So you can get a spectral line, an absorption line will split into two if it is acted on by a magnetic field. That is how we figured out that sunspots are magnetic. We started taking a spectrum across the sun, you know, looking at the sun, you cross into the sunspot, and all of a sudden the spectral lines will split. And so that was the indication that, oh, that's a magnetic thing. Yeah, I'm seeing some stuff in the chat about electron spin. I will look that up and we will get you some resources, but these are such good questions.
Yep, the electron spin is related to the velocity also of the atoms themselves.
Perfect. Yay. All right, so ways that we view spectra, and yikes, it's quarter of. How did that happen? Okay, so a prism will split light and the light will pass through it and it will work its way into a rainbow. We have a couple prisms out at the observatory so that we can let the sun shine through them, make rainbows. There's the one that hangs from the ceiling that makes rainbows on the wall. There are a couple that you can hold. These are really fun for kids that find the rainbow on the floor and want to catch it. But it's also an opportunity to talk with visitors of various ages about what the spectrum looks like and the fact that sunlight is white light that contains all of the colors of the rainbow. All right, so another way that we view spectra is through diffraction grading. So this picture was taken through a diffraction grading, looking at an element. This is neon at our Discovery Station. So here's the light source. We're looking through the diffraction grading, and it has spread out. These little copies of the light break into colors. So we have a whole bunch of reds, a bunch of oranges, some yellows, a couple greens, and a blue or two that are very faint and hard to see. It splits it in a mirror image, so it will send that spectrum out on either side. And now I am going to attempt something. We're going to see if this works. So I'm going to bring back my video and actually stop the sharing because, of course, I brought home a diffraction grading because I'm just that nerdy. So we are going to see if I can get this centered. And I tried this earlier, it kind of works. So what I'm showing you is a LED flashlight. Right. I was gonna try and get a thing to hold this for me and I didn't have time. All right, so as I move this away, you forget it over here. So there's a little bit of rainbow action going on the side there. As I move it farther away, the light and the color spreads out more. But because this is an LED, it's really hard to tell. But this is not a continuous rainbow. This is little copies of the light. So I'm seeing a chunk of red, yellow, green, and blue. And if I turn it, the LED flashlight has 3 little dots of light. And you can kind of tell that I'm turning it a little bit. So the image that the diffraction grading shows is going to be a copy of the shape of the light source. And yeah, if I can get it even farther away. Yeah, so that was our fun with diffraction gratings. Now I will go back to the screen share. All right, so in the Spectra, of course, we have people using the diffraction gratings at the Discovery Station. These are the easiest way because you can hold it up to your eye and you can see your own personal copy of the spectrum. This here is the Mercury, and over here we have sort of the orange, the chartreuse green, and the blue on either side. So when we run the Discovery Station, this is how people see it. All right. Now, how diffraction gratings work. A diffraction grating is literally just a sheet with a whole bunch of slits in it. And because photons move in waves, as photons slip through each of these little slits, they move outward. Each of those little waves from each slit then starts running into the ones next to it. They start constructively and destructively interfering with each other, like if you had ripples from 2 different places on a pond and they start running into each other. Some places they add up and build, some places they subtract and make lower. What ends up happening, this is a very simplified view, is that based on the placement of the slits, the way that the little photon wavelengths run into each other essentially turns the entire wavefront this way. Now, at the same time, there is also one that's turning the other way symmetrically. But it is the light slipping through these little slits, interacting with itself, which will spread it out to one side and will spread it apart, split it into its different colors. Pulling up the chat again. Yep. All right. So that is the very simple version of how diffraction gratings work. If people want to ask, the one that I was holding was 500 lines per millimeter. 500 little slits per millimeter. I'm amazed this stuff actually holds together, but it's great. Most of the ones that we use are about the same. So we view spectra through spectroscopes or spectrographs. People often ask me if those 2 words are interchangeable. They essentially mean similar things. A spectroscope is something that you look into. So this is our little spectroscope. Genevieve brought it to the winter star party in Florida, hence the palm tree. But a spectroscope is something that you look into and see the spectrum. A spectrograph takes the spectral data and puts them into either a graph or a chart, or it takes the information, but it's something that you are analyzing in the form of data rather than looking at. So the one that we use at the observatory is a spectroscope because we're looking into it. All right. So, quick pop quiz, name one thing. What can a spectrum tell us about a star? I've seen a few notes about this from various people, but there are so many wonderful things we can see. All right, yeah, so elements, what it's made of, composition, yep. Temperature, yep, temperature is a big one. Phase or age, yep, we can interpolate the age from the spectrum. Radial velocity to find and confirm exoplanets, yep, so motion, whether it's moving toward us or away from us. Yes, indeed. All of the above and more, because we can interpolate even some other stuff. Yep. All right, so main things that I love to tell people we can figure out from the spectrum: the chemical composition using that absorption or emission fingerprint for each element, like we talked about. We can get the temperature. I'm going to go into that in a little bit. That's based on how much of each wavelength in the sort of background continuous spectrum we see. We can figure out mass and age based on looking at lots of stars and how they tend to move through their life cycles, how their spectra change. Mass is generally figured out based on luminosity, and we use temperature to inform that as well. Relative motion, so that's, is it moving toward us? Is it moving away from us? And that can be useful for stars. That's also really useful for galaxies. If I take a spectrum across a galaxy, if on one side I see that it's moving away from me at a certain speed, and on the other side I see that it's moving toward me at a certain speed, now I know, A, that that galaxy is spinning, I know which direction, and I know how fast. All from patterns in light. And you can tell if a star has a companion star. About 70% of stars in the sky are binaries, 2 or more stars orbiting around each other. Usually they are close enough together and or far enough away that you can't see the 2 separate stars. But if you see the spectrum changing in a regular way, you can figure out that it's 2 different stars. And you can figure out their masses based on how they move, which is pretty awesome. And yes, the radial velocity of a star, we can also use that wobble, that motion, if it's moving toward and then away, and then toward and then away, and sort of moving in a circle, we can tell that based on the measurements that there's a planet orbiting around that star and pulling on it with its gravity. All right, so this is a baseline stellar spectrum. This is an absorption spectrum, so here's what it looks like. Up top, so we've got the red, we've got a big hydrogen, so we've got big hydrogen absorptions, but we've got a few other gases in here for flavor also. So you can look at where the colors are missing. You can also look at which colors are the brightest. Are they all about the same brightness, or do they seem to actually be brighter at a certain place along the spectrum? That can be hard to do by eye. So down here is a chart of the same information. The line is how much light, or what's the intensity at these different wavelengths. This is in micrometers, I think, because it wouldn't be nanometers. So we have each of these little dips is one of the absorption lines, one of those dark black areas. But if we ignore the little dips and the black, for the black absorption lines, and we just look at the overall curvature of it, it's not flat. It's not that bright in the red. It gets a little brighter into the yellow and green. It peaks over here in the blue, and then the general brightness drops off again. This curve, for those of you who remember your physics, this is a black body curve. So a black body is an object that can absorb all wavelengths and emit all wavelengths. It's not going to absorb and emit the same amount of each wavelength. Which wavelength it peaks at, which one it is emitting the most of, is a function of temperature. So this is how we figure out temperature. You look at the overall, and you look at where is it the strongest. This particular star being strongest in the blue here, first of all, would look somewhat bluish to our eyes, and that would mean it's rather hot. Because we talked about earlier, shorter wavelengths, purple and blue, higher energy, red, lower energy. This is why cooler stars look redder and hotter stars look bluer or even purple. This is similar also to why the blue part of a flame is the hottest and the yellow and orange and red parts of the flame are cooler toward the edges. Now there is also an element, flames can change color based on the chemistry that's in them, but generally speaking, if you don't have something in there like sodium that's going to put a bunch of yellow into the flame, you can look at the colors of things and how they are glowing. So red hot, and then blue hot is hotter. White hot just means it's in everything really brightly. All right, so different types of stars with different spectra and temperatures. So again, here's the chart of how much light we see, and here's how it looks. So for a sun-like star, it peaks, its black body curve peaks in the middle of the spectrum around the green and yellow. This is part of why the sun looks yellow to our eyes, although really the sun looks yellow because we're seeing it against the blue atmosphere. The sun is strongest in the green-yellow, and it peaks right in the middle of our visible spectrum. That is not a coincidence. As little creatures that evolved on the Earth under the light of our sun, our eyes developed to be most sensitive and to have our visible spectrum be centered on where our star is the strongest. Now over here, Sirius A, which is a blue supergiant, it is brightest in the blue. So it does look a little bit bluish to our eyes, even though it's continuous, it's making all the wavelengths. If it's making a lot more of one color, our eyes will perceive it as being more that color. But again, that's because our visible spectrum is centered for our star. If we were born on a planet orbiting Sirius, blue would be the center of our visible spectrum. We'd probably be able to see into what is ultraviolet, and we may lose some of the reds and certainly the infrared. All right, Aldebaran is a red giant, so its peak is over here in the red, and it looks reddish in color for the same reason. So these are all black body curves. So this is how, for cosmic survey, for any number of the activities that we do that deal with this, the way that we figure out temperature based on color is this black body curve. I don't think ever said the word black body to a visitor because it gets into complicated physics, but the color something looks, if it's glowing in all the colors, if it's stronger in one color, that's going to correspond to its temperature. All right, so this is essentially the Doppler shift. This is that radial velocity in motion, and I'm running out of time. If you have a light source that is moving toward you, it's putting waves out in both directions. But if the object is moving, those waves are getting compressed on their way to you. So the effective wavelength of that thing, whether it is light or sound, is going to get compressed. In sound, this is why an ambulance sounds higher in pitch, higher frequency sound wave, when it's coming toward you. And then once it passes you and it's moving away from you, it is stretching those sound waves out into a lower frequency and a lower pitch. With light, if it's moving toward you, compressed shorter wavelengths will look more blue or purple. We call this blue shift. Things moving away from you will get stretched into longer wavelengths and will look more closer to the red. Now that doesn't mean that something in the sky that's moving away from you will look red in color to your eye. But if you are looking at the spectrum, you'll see that little hydrogen line that's in the red, but it may be a little farther, it may be a little bit closer to the infrared than it should be. So a big part of looking at the spectrum and those absorption lines is not just what exact color or wavelength is it, but how is it spaced from the others, because you have to use that to figure out which line it is you're seeing at all. Okay, is the animation coming through? Are the two little stars orbiting and moving around each other? Okay, good. So I like to leave this one up for a whole lot of rounds so that you can kind of take it in. We have two stars, A and B. A is a yellow star, B is a bigger red star. So I want to, hi River, my cat's being opinionated. So it's so not dinner. What is wrong with you? All right, so let's look at B, the big red star. So right now it's moving away from us. Each time it moves, the little arrow points to what is the spectrum that we would see. This is a binary system. So right now, B is moving away from us. So B's spectrum here is shifted toward the red from where it should be. So right here, again, it's moving away from us, it shifted toward the red. Now we just kind of see both stars. Now it's coming towards us. So that same B spectrum now is blue shifted. So depending on where these two stars are in their little orbits, one of the star spectra will be coming towards you, blue shifted, one will be away from you, red shifted, and they will switch. So you'll see, and again, A had a thinner absorption line, so that's how you can kind of tell which one is which. They overlap, and when they overlap, you're really mostly, when they're eclipsing each other like this, you're only going to see the spectrum of the closer star at that point. So if you see this pattern of, I see the spectrum of A, spectrum of B, and then I see B blue shifted and A red shifted, and then I just see the spectrum of A, and then I see A red shifted, B blue shifted. This is what eclipsing binary spectra look like. So I love this animation. I like to leave it up for long enough that you can sort of absorb it. There's some text, but yes, this one is assuming that it's just showing hydrogen, so it's just showing the hydrogen alpha, beta, and gamma lines, the red, the cyan, and the blue. So yeah, here it is assuming that they have the same basic, the same elements in them. What's different is the width of the absorption lines, which in this is accentuated. They don't usually look this different, but this is showing you for the two different stars, the proportion of hydrogen to, say, other elements might be different. So the relative widths of those absorption lines, the hydrogen in star A and the hydrogen in star B, might look a little bit wider or narrower. Yeah. All right, so applications real quick. When an exoplanet crosses in front of a star, you will see the shadow of it, but you may also see more absorption, say, in the methane part of the spectrum or in water. That can tell you what's in the exoplanet atmosphere. Some museum connections real quick. So this is the Decoding Starlight Discovery Station, again, photographed through a diffraction grading. So visitors can do this themselves. This is the Mills spectrograph, I believe, which is in the spectroscopy section of Explore the Universe. Phoebe Waterman-Haas, our namesake, used this one. This is what she used to do her dissertation research, first woman allowed to make her own observations for a PhD, in the United States at least. At the solar wall, whether indoors or at the observatory, when we're talking about the ultraviolet and these different, each of those filters is looking at one particular emission line, usually for a variation on iron, but a couple are helium. So you can tell people that each one is looking at a different piece of the spectrum. There are emission lines in other ends of the spectrum. Yes, so what the Solar Dynamics Observatory sees here, these are emission lines in ultraviolet, extreme ultraviolet, and there's a couple that are in the X-ray. Again, the hands-on spectroscopy, we're limited to our visuals, but spectrographs and detectors can take in spectral emissions and measure them at any point along the electromagnetic spectrum. X-rays are a little weird because X-rays will go right through things, so you have to angle it. The X-ray has to come in at a very low angle so that it will bounce off it like a mirror rather than going straight through it like it does through your bones. And finally, of course, our little spectroscope out at the observatory, which looks at the sun. It has the controller on the side where you can scan through the different lines, and it's got a marker on the side so that as a visitor or you sees one of those thick absorption lines, you can see what it is that you are looking at. And we have like -2 minutes. Questions?
Thank you all so much. Shauna and I will stick around for about 5 minutes or so to answer any follow-up questions. But thank you all again so much for coming out and talking to us a little bit about spectroscopy. Don't forget we have another one next week at noon on Wednesday. If you have any questions, comments, anything else you'd like to share, you can always email us at siobservatory@si.edu. That's siobservatory@si.edu. So we look forward to seeing everyone next week.